So this is ELC111, and the topic of this presentation is digital electronics. Now let's start by defining what we mean by digital and analog quantities. And the best way to do this is to illustrate what we mean by analog quantities as sketching a simple ramp. And if someone were walking up this ramp, then this person can be anywhere from the ground, or what I'll call height 0, up to some height we'll simply define as h. So as this person moves up the ramp, his height will increase, but there's no set or discrete positions or points where this person can be above the ground. Conversely, if we think about a digital system, then the digital system has discrete or set points, such as we find with a set of stairs. So if a person's walking up these stairs, oops, his head's too small. Then this person can either be at ground level or height 0, or can be up at some height h, but there's discrete points at which this person has to be. If they move up the stairs, they are either at step 1 or at step 2 or step 3. So a digital system has discrete values or discrete levels, whereas an analog system can be any value between the limits 0 and, for this example, the height h. So we think about analog quantities, and of course we see an example of height, but another example of an analog quantity would be time. Time is a continuously varying quantity. There are no set points or set levels. However, we can digitize time if we think about days or minutes or hours or seconds, and we can break this down into smaller units of milliseconds and microseconds and nanoseconds. Another analog quantity would be pressure. Another analog quantity would be pH. Another analog quantity would be mass. Another analog quantity would be temperature. And we could have this list go on and on and on. And of course, we quantize or digitize all of these analog quantities into units. They could be, for instance, pressure could be bars, millibars. They could be milligrams of mercury. pH, you might remember from chemistry class, is expressed in discrete or quantized values. Mass can be in pounds, grams. Temperature in degrees, either Fahrenheit or Celsius or Kelvin. Now, for our discussion here, we're concerned about the analog quantity of voltage. And of course, understand that we can quantize voltage, because voltage is simply the difference in charge, or the absence or deficiency of electrons that exist at 2 points. However, for most applications, we think about voltage as being a continuously varying quantity. It can be anywhere between some value and the upper limit. For example, with voltage, we think back to the second or third week of the semester when we talked about the construction and application of a potentiometer. Let's put a little ground here. So if we have a source voltage over here that's 5 volts, and we connect to that 5 volt source a potentiometer, then my output voltage, V out, with respect to ground, can be anywhere from 0 volts to 5 volts. As I vary this potentiometer, this output voltage could go from 0 volts up to 5 volts. There are no set or discrete points that the output voltage can be. And then as we progressed on through the semester, we saw that with voltage, we also have continuously varying voltages with respect to time, in that we can have a voltage that increases to some positive maximum, the peak point, and can decrease to some minimum value, the negative peak point, and then of course back to 0. So our analog quantities can be varied between 2 limits, and those limits are a function of the position of the potentiometer, or these voltages could vary as a function of time or be continuously varying. Now, for our digital voltages, we have only set or discrete values. If we look at digital voltages as, and here on this graph we're going to have voltage, the voltages can either be 0 volts or they can be 5 volts. They can't be anything in between. And this 0 volt condition is considered to be what we term to be a low logic level, and the digital value of 5 volts is considered to be a high logic level. So with a digital system, our voltages can either be low or high. They can either be 0 volts or 5 volts. They can't not be some value in between 0 volts and 5 volts. Now, with respect to digital electronics, this low logic level is considered to be a logic level of 0. And a high is always considered to be a logic level of 1. So with our digital systems, excuse me, our voltage values are either 0 volts or 5 volts. They're either low or high. They're either a 0 or a 1. Now let's talk about numbering systems. Now, we're all mostly familiar with the decimal numbering system. And with the decimal numbering system, we have 10 symbols to represent quantities. And of course, if we have no items, and what do you want to count? You want to count, let's count jelly beans. Okay, so let's count jelly beans. And if we have no jelly beans, this has a decimal value of 0. And of course, if I've got one jelly bean, I'll have a decimal value of 1. If I have two jelly beans, excuse me, I have a decimal value of 2, 3, 4, 5, 6, 7, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. And of course, if I have 10 beans that I'm counting or quantifying, after I get to 9, I've run out of symbols that represent quantities because I only have symbols from 0 to 9. So now I have to put a 1 in the second column and a 0 in the first column. Now in our decimal numbering system, our units, this value right here is worth 10 to the 0 power, or 1. And of course, this column has a value of 10 to the first power, or 10. And if we were to continue counting jelly beans, we would at some point need a third column, and every unit, every value in this column would be worth 10 to the second. So for example, if I had 2, 3, 1 recorded, this would equal 2 times 10 to the second plus 3 times 10 to the first plus 1 times 10 to the 0, which would of course equal 231. Now I know this all seems like duh. Yeah, we do this all the time. But when we think about digital electronics, we only have 2 symbols to represent quantities. So this is what's called a binary numbering system, because we've only got 2 symbols to represent quantities. We've either got what? A 0 or a 1. We don't have anything else. So if we start counting in binary, if we don't have any beans to count, we of course have a 0. And if I've got 1 bean to count, I've got 1 bean. But when I get to 2 beans, I don't have another symbol to represent quantities. So I have to then have a 1 in the second column and 0 in the first column. That this value in binary equals 2 in decimal. And if I count to 3 jelly beans, well, I can put a 1 here and a 1 here. So this would equal, of course, 3 in our decimal numbering system. Now, if I add or count 1 more bean, well, gosh, I've run out of symbols to represent quantities. So I now have to put a 1 over here and a 0 here and a 0 here. So in binary, 1, 0, 0 would equal 4 in our decimal system. If I add one more jelly bean, well, I can put a 1 over here. This would equal 5. And if I add one more, I can't put another symbol over here. I have to then put a 1 in the next column, which would equal a digital value of 6. And we can keep going all the way down here to 10. 7 would be 1, 1, 1. 8 would be 1, 0, 0, 0. 9 would be 1, 0, 0, 1. And 10 would be 1, 0, 1, 0. So if we look at this binary numbering system, every digit in this column is worth 2 to the 0 power, or 1. Every 1 in this column is equal or worth 2 to the first power. Every 1 here is worth 2 to the second power. And every 1 over here is worth 2 to the third power. This is really not that much different than we had with the decimal numbering system. It's just that now with the binary numbering system, we are limited to having only 2 symbols, a 0 or a 1. For example, then, if we have this binary value of 1, 1, 0, 1, then this value would equal 1 times 2 to the third plus 1 times 2 to the second plus 0 times 2 to the first plus 1 times 2 to the 0, which would equal in decimal 13. And I'll put a little 10 down here to show this is a decimal number, or base 10 is what we call this. So every 1 here is worth 2 to the third, or 8. Every 1 here is worth 2 to the second, or 4. Every 1 here would be worth 2 to the first, and every 1 here is just worth 1. So we ended up with 8 plus 4 plus 0 plus 1. Now, most of our computer systems operate on digital values in groups of 8 or groups of 16 or groups of 32 or groups of 64, and even in some cases groups of 128. Now, when we talk about our computer systems, our decimals or our digital systems, we use the term bit, excuse me, to describe or discuss an individual 0 or 1. Put a slash there. Let's make that bigger. 0 or 1. So a bit is just simply a piece of digital information. It's either a 0 or a 1. We use the term byte to equal a group of 8 bits. And again, we do this because most of our computer systems or our digital systems group together these zeros and ones in groups of 8 bits or 16 bits or 32 bits or 64 bits. Now, we also can think of these bits together in 4-bit groups. And they use the term nibble because a nibble is a small byte. And if a byte is 8 bits, a nibble is, well, I guess it's half a byte or only 4 bits. So the term bit, again, is just a single piece of digital information, either a 0 or a 1. A byte is an 8-bit group, and a nibble is 4-bit groups. Now, when we look at expressing these decimal or digital values that are either 8 bits or 16 bits or 32 bits or 64 bits, appreciate the fact that if we had some 8-bit string of zeros or ones, such as 1, 0, 0, 1, 1, 1, 0, 1, that it would be difficult. We would be prone to making errors if we had to record this information simply as a series or string of ones and zeros. Now with 8 bits it's not so bad, but we start getting 16 bits or 32 bits or 64 bits, then it's problematic to say the least. So what we do is we group these bits together in 4-bit groups. And we do this simply to be able to express or record these values in a simpler fashion. Now, with 4 bits, we can have values that range anywhere from 0, 0, 0, 0. And we'll just count here in binary as we did a second ago. Make sure I don't make a mistake. Oops, I did already. Am I going to run out of room? I hope not. There we go. Good. I fit them on the page. By grouping these bits together in 4-bit groups, you'll note that we have 16 possible combinations of zeros and ones. And with 4 bits, 4 bits, our possible combinations are going to be up 2 to the 4th power, which equals 16 different combinations of zeros and ones. So what we do with, and this is why we call this, of course, a hexadecimal numbering system, because hex for 10, or excuse me, hex for 6 and decimal for 10, this is what we call in mathematics base 16. That again, we have 16 possible combinations of zeros and ones with a 4-bit group of ones and zeros. So let's count these values up in what we call hex or hexadecimal. So this, of course, would equal a decimal equivalent or a value of 0. This would equal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And what am I going to put here? Because I've really, oh, that's not right. I made a mistake. So what are we going to do next? Because I don't really have a symbol to represent 10 units. I can't write 1 0 like I did just a second ago because, well, I'll show you that in just a minute. So we need another symbol to represent this particular quantity. And what we use now is the letter A. This quantity would be represented with the letter B, C, D, E, and F. Now, when we look at our hexadecimal numbering system, just like we saw with our decimal numbering system and with our binary numbering system, each unit in the first column is worth 16 to the 0 power. Each digit or number in the second column is worth 16 to the first power. And each number would be in the third column would be worth 16 to the second power. So this is why right here I could not represent this quantity with a 1 0, because this 1 0 would represent 1 times 16 to the first power plus 0 times 16 to the 0 power, which would equal, of course, in decimal, a value of 16. And this can only represent a value of 10 in decimal, so I cannot record this as a 1 0. I have to use a new symbol to represent a quantity of 10 decimal items, because again, I've run out of symbols after 9. I have to start using the letters H. So let's go back up to my example that I had here. If we have an 8-bit binary value, 1001, 1101, that to express this, and again, this is my binary value, and if I want to express this group of zeros and ones, this binary value in hexadecimal, I simply look in my chart and see that a 1001 is the symbol 9, and 1101 is the symbol D. So this 8-bit binary value would be equal to 9D, and we usually put a letter H behind this to tell us that this is a hexadecimal value. We don't put a 2 here for binary. We could, but the 2 is just implied. Now, if we want to convert this binary value or this hexadecimal value to a decimal value, then of course this 9 would equal 9 times 16 to the first power, and the D would represent what, 13 times 16 to the 0 power, which, let me get my calculator, 9 times 16 plus 13 would equal 157 in decimal. So with our numbering systems, of course, we started by looking at decimal numbering systems. And of course, we counted up some jelly beans in decimal from 0 through 9. After 9, we ran out of symbols to use to represent quantities, so I had to put a 1 in the second column and 0 in the first column. And in binary, a binary numbering system, or what we call base 2, we've only got 2 symbols to represent quantities. So when I go past 1, I have to then put a 1 in the second column, and of course a 0 in the first column, and then we have 3 and 4 and 5. But in most computer systems, we group together bits in either 8 or 16 or 32 or 64 bit groups. So it's easier to express these digital quantities using the hexadecimal numbering system, base 16. Because with 4 bits, we have 16 possible combinations of zeros and ones. And again, it's easier to record these values, express these values using the hexadecimal numbering system rather than the binary numbering system when we have 8 bits or 16 bits or 32 bits or 64 bits.